Alrighty, picking up right where we left off. So we're going to continue working on this Gearbox project. We are going to move forward and figure out the dimensions of our shafts, model the standoffs, get those in the assembly, download one other part we're going to need, which I'll talk about later, and then we'll put in all the fasteners and everything and make the gearbox look realistic and look at weight. Okay, so let's start with the cluster shaft because it's easiest. And let's talk about the... Actually, let me back up here. Let's back up. Let's not start there. Let's start with the standoffs. So the reason we're going to start with the standoffs is I mentioned before that this, right at the end of the last video, that the constraint that we created between this bearing and this gear was going to be temporary. Now, the reason for that is will become apparent in a minute. So I'm going to press the M key here, which brings up the measure tool. There's a button for it somewhere. Yeah, under Tools, Measure, if you really want to click the button. I just use the M key. So this will allow you to measure the distance, the length of things. I can click this line here. It'll tell me the length of the line. All right, 2 3/4. Or I can click two things, and it'll tell me the distance between them. So I'm going to click the inside of my gearbox plates. Okay, so you'll notice this is 1.121 inches. All right, I can tell you right now that this should be 1 1/8 inch. Now the reason it's 1.121 is because of what we're going to call rounding errors. So this bearing is modeled, right, and they have to type in a dimension. Now this is supposed to be a 1/16 of an inch, right, but it's probably modeled in a system that's in metric or something, and it's probably rounding it down to 0.062 instead of 0.0625, right? So you're losing a 1/2 thousandth of an inch here, 1/2 thousandth of an inch here. The gears should be 1/2 an inch overall width from end of the hub to the end of the opposite hub. You know, so this should be an inch total. You should have a 1/16 of an inch here, and you should have a 1/16 of an inch here. So it should be 1 1/8 inch overall. But because of slight inaccuracies in the dimensions of the CAD model when the CAD model was made, you get this like error stack up that makes this dimension several thousandths of an inch different than what it should be. So I know, just because I know the widths of these different components, and you could look these up on Vex's website if you wanted, or you can measure them individually and then just kind of try to figure out what the actual value should be. You want to be careful when you do that, when you assume that a part is a different dimension than it is in CAD, and you'd be okay assuming that 1.121 inches is the correct width. I'm not comfortable with that, though, for a couple of reasons. First of all, I know what the values are supposed to be, and if you get the real world parts and they're actually a little wider than they are in CAD, which can happen, it'd be pretty tight in here, and you'd be compressing the bearings and putting some load on those, which you don't want. In addition to that, you want these to be a little bit loose anyways, so even if they aren't oversized, it'd still be nice to have just a few thousandths of an inch of slop. So what we're going to do is we're going to make this 1.125 inches. Now, this goes back to what I was talking about that constraint that we created earlier. Just going to escape out of that. That constraint that we created between here. It's temporary. I don't want these two things to be constrained to each other. I want the length of the standoffs to actually define how far apart these plates are. I don't want this constraint to define how far apart these plates are, because right now the plates can't move. And if I make a 1 1/8 inch standoff and put it in here, it won't let me constrain the ends of the standoff to the two plates. It'll give me an error. So what I'm going to do is I'm going to delete. Now that we've put this in here and we've measured it, right? We know what the measurement should be. I'm going to go in and I'm going to delete this constraint back out, and then the plates will be able to float again, and then we'll put the standoffs in, and the standoffs, once we constrain the standoffs, that will hold this plate in place. So I'm going to go in here. I need to find which part this is over here in the browser, so I'm just going to click on it in one of these two. It can be either one, so I'm going to click on the bearing, and you can see it highlights here in the browser. So I'm going to click the drop-down arrow. Now, here's a list of the constraints that this bearing participates in. There's 4 of them. Now I know just because that was the last constraint we placed. It's going to be this bottom one. But if you look at it, you can hover over each of these, and it kind of shows you one selection will be red and one selection will be green. It'll show you what the different constraints are. Like this one's the one that we constrained the center line, right? We constrain the outside of the bearing to the inside of the hole. This one we constrain the inside of the flange to the inside of the plate. This one's this gear, the work axis of this gear to the work axis of the bearing. And this is the one that we're interested in. So I'm just going to right click on that and delete it. And if I zoom back out, now this can float again. Okay, so that's what I want to talk about there. So we're going to go model the standoff. So I'm going to go create new standard.ipt, click create. All right, so the standoffs are going to be made of 3/8 round aluminum rod. That's what we typically use on Stellar Robotics. Different teams, use different stuff. That's what's worked for us. So we're going to create a circle that is 0.375, which is 3/8. You could also type in 3 divided by 8 if you wanted to. We're going to press enter. We're going to finish the sketch. Okay, we're going to extrude this, and now this is where we set the length. So this is the gap that we want between those two plates, because that's what the standoffs do, is they hold the two plates a set distance apart. So this is going to be 1.125. Now we're going to click OK. All right, so now we need threads in this. So we're going to, if we go back to our assembly here real quick, and I'm just clicking on these tabs down at the bottom to switch back and forth between these things. I don't need that anymore. You can click little X arrows if you want to close files that are open, by the way. All right, so there's going to be a screw out here that goes through this hole and threads into the standoff that's going to be in here, and then same thing on the other side. So we need a threaded hole in each end of this standoff. Okay, so we're going to do that. We're going to use the hole feature. The hole feature can create threaded holes. So we're going to create a sketch on the end of this. Now we need a center point to locate the hole. So we're just going to place the center point on the origin point that's automatically in there, and click Finish Sketch. That's all we need to do in that sketch. So then we're going to hit the hole button. Now down here where we select kind of the type of hole we're doing, it's going to be the third one from the left. It's going to be this one's kind of got these weird dotted lines in it. That's threaded holes. Now we're waiting for this to load. Like I said before, the first time you do like each of these, it takes a while to load. Now that's loaded. We need to set the termination not to through all, because this standoff, with the size of screw that we're going to use, I mentioned in the first video when we were doing the layout sketch, I mentioned that they were going to be number 10 fasteners. You can only tap about a ½ an inch deep with a number 10 fastener, and that just has to do with the tap, the tool that you use to make the threads. So you can only get about a ½ inch deep of threads, so we can't go all the way through this standoff with one set of threads. We're going to have to actually tap it from one side and then tap it from the other. So we want our termination to be distance, okay? And then once we select the thread type, it will automatically fill in the maximum thread depth that we can have. Inventor just stores that information, so we don't have to know what it is. So we're going to go under here, under size, we want to make sure we're under ANSI unified screw threads in the thread type. And then under size, we're going to scroll up. There's a lot of threads in this list, so don't get lost. It's going to be 0.19, and in parentheses it says number 10. Okay, that's what we want. So click on that. Now under designation, we're going to use 1032 screws. So you're going to click that and go down to 1032. It says UNF. It's not important what that means at the moment. And you'll notice it automatically changed the depth of the hole to 0.536. Notice this full depth checkbox is checked. If you uncheck that, it will not run the threads the full depth of the hole, which is what we want. So click full depth and click OK. Now rotate around to the back end of the standoff, and we're going to just repeat that exact same process because it's 2 holes, 1 from each end. And click that, click there, make a sketch, create the point, place that, finish the sketch, create the hole feature. The whole feature, like a lot of dialogues in Inventor, will remember the settings that you had used last, so you don't need to change anything. It'll be number 10, it'll be 1032, distance, full depth, and the right dimension. So click OK. Now the holes will meet in the middle, right? They will meet a little bit in the middle, and that's okay. In reality, we have a little lathe in our shop, little benchtop lathe that we typically make these standoffs on. And typically what we do is we actually drill through, because what you do when you make a threaded hole is you drill with a smaller drill than the actual threads, and then you take the tap, which is the threaded cutting tool, and then you run the tap in to actually cut the threads. So what we typically do is we actually drill all the way through, because a drill bit is long enough to go through this, and then we just tap from either end. So in reality, there's going to be a hole that goes all the way through this, but it's just not going to be tapped. There's going to be a little space right in the middle of this that's not going to have threads, which is fine. So this is realistic enough. When we make the drawing for this and give it to the machinists, they'll know what they need to do. So we want to create a work axis on this just because it makes this easier to constrain. Not super critical for this part specifically, but I usually do it for consistency. So I click axis and just click on the outside. This is going to be aluminum 6061, so we'll set that material here. We're going to go ahead. I think I have a special one. Yes, just for me. Your inventor won't have it, but I have a stellar yellow. It's a color that's pretty close to the paint that we use that's yellow on our robots. You don't need to change the color. I'm just doing it because I want to, because it looks cool. Okay, so I'm going to save this. I'm going to give it the next sequential number here, and save. All right, so we're going to place this in the assembly. So we're going to go to place up here in the corner. We're going to go and select this part. Everything's syncing to Google Drive right now, but that's okay. So we're going to place, this orientation is right. So we're going to place 4 of these down, and we're going to constrain all of them pretty quickly. So we're going to place one here, near this corner, one near that corner, one near this corner, and one here. Okay, I'm going to escape out of that because we're done. So I'm just going to rotate around and grab this work axis, click that, and click this hole. Okay. Now, I could constrain this work axis to this hole, and I wouldn't actually get any errors from that. But I would be creating redundant constraints because this plate can only move in and out, right? I already placed those flush constraints between the edges of the plate, so I don't need to constrain the standoff between itself and this plate. I just need to constrain the standoff on one of the 2 holes. Now, I could constrain it to this plate if I wanted. There's nothing special about constraining to this plate versus this plate. The only reason I'm doing it to this plate is because this is the plate that's grounded, so it just makes more sense to me to attach the parts to the grounded part rather than the part that's not grounded. That's what I'm going to do. So I'm going to go through and do that for all, oops, not place, constrain. I'm going to do that for all 4 of the standoffs, put them in their respective hole, grab the work axis and find an angle, work axis to the hole. Okay, so now what I'm going to do, I'm going to pull these out, and then I'm going to constrain the back faces of these to the face of the gearbox, right? Basically butt them up against the gearbox plate. So I'm going to find the constraint tool, rotate around, do these real quickly. So select each one, hit enter, select each one, hit enter. All right, so you can do this pretty fast if you get good at it. You select both of them. Okay, so now we've got those all butted up against the plate, which is great. So now, basically what we want to do is we just want to constrain the ends of these to the inside of this plate. However, for the same reason that I listed that we didn't constrain the center line of this to here, we only need to do one, right? We don't need to constrain all 4 of these to the inside of this plate because these are all the same part, right? They're all the same length. So if we attach the inside of this plate to the end of this standoff, we know the inside of this plate is going to be in line with the end of these standoffs too. So we only need to do one. So we're going to do that. So we're going to constrain, take the inside of the plate, and we're going to go to the end of the standoff and apply. Okay. And I just picked the paint job because this is how on Stellar we would paint these parts typically. We typically do blue for the large structural components and then yellow for some of the like highlight parts and support braces and stuff, and it usually looks pretty good. Okay, so now we've got the gearbox mechanically, like the structure of the gearbox is done. So now we've got to add in the shafts and go do all that other stuff. So I'm gonna make sure I save this. So if I lose power or something, I won't lose my progress. Now, we're going to start with this shaft here. So let's talk about that a little bit. We've got hex bearings, okay, 3/8 hex. We've got a 3/8 hex hole in this. We got a 3/8 hex hole in this gear, and we got a 3/8 hex hole in the opposite bearing. Okay. Ideally, you want a shaft. Now you'll notice because each of these things can like free rotate. Okay. The hexes aren't lined up. Once again, that's not important because all we care about is the center line. But anyways, typically you want your shaft to be touching the full inside length of the bearing, right? You wouldn't want to stick a shaft halfway in this bearing and that be all the support you have, right? You want to utilize the full width of the bearing, the full depth of the bearing, really, to support your shaft. So basically, the end of the shaft is going to be flush with the outside of this bearing. The other end is going to be flush with the outside of this bearing. Okay, so because we have 3/8 in all the way through, it's going to be 3/8 hex all the way through. We can just model a piece of 3/8 hex shaft that is the length from the outside of this to the outside of this. So we can use the measure tool. I'm going to press the M key. I'm going to measure from the outside of this bearing to the outside of this bearing, and it's 1 5/8 of an inch. Okay, that's a nice fractional number, which is what I would expect because it's 1 1/8 inch. These are 1 1/8 inch long, and each of these plates are 1/4 inch thick, so that adds up. And the bearings are designed to be flush with the outside, so that checks out. That's what it should be. So it's 1 5/8. We'll just remember that, or keep a piece of paper and write it down if you don't want to try to remember this stuff. Another thing that I do typically is I'll open a notepad window, and if I have dimensions that I need to measure and then go model something, I'll just type them into a notepad document, just so I don't have to juggle pens and paper and stuff at my desk. I can just use the computer. And also, if you get weird numbers that you don't want to try to type in, you can also copy and paste, which is nice. Okay. That's all just, there's nothing that's critical. It's just little workflow things I've figured out over the years that I do for myself. You can figure out what works. So we need to model a hex shaft. So we're gonna create a new part here. Standard, create. Okay, so under the rectangle drop-down list, click the arrow. We're going to go down to the bottom and click polygon. There's already 6 sides, right, which is what we want for a hexagon. So we're going to click to place the center of the polygon in this origin point in the sketch. We're going to just take it out here and place it down. And then we're going to press escape to get out of the polygon tool. Now I'm pressing F9 because those little yellow dots in the corner show up. I press F9 to hide those. And then if you'll notice, I can like spin this around. I can change its size, which will fix with the dimension, and I can also spin it, which is not what I want. I want one of these sides to be like straight up and down or straight vertical or something so that I can't spin this shape. So I'm just going to use a vertical constraint, and I'm going to click one of the sides and just make it vertical. I'm going to escape out of that. So now I can dimension this and make it the size that I want. I'm going to dimension flat to flat, and this will be 0.375, which is 3/8 of an inch, or I could also do this, 3 divided by 8. Press enter. Okay, so that's all we need there. So we're going to finish the sketch. We're going to extrude this out to be 1.625. That's 1 5/8. If you wanted to type this in, you could not do 1 space 5 divided by 8, right? This is 15 divided by 8. Actually, give me a second here. Okay, that actually does work. I did not realize that worked. Okay, you learn something new every day. Okay, I did not realize that. So you can do that. Never mind. I stand corrected. Anyways, so you can type in the fractions like that if you want to. I was going to show you a different method, but that works. All right, I never use fraction. I always use the decimals just because that's how I've always done it. All right, so we have a problem. If we go to our assembly, and we've got these work axes, right? We need to constrain this shaft in here somehow. We've got these work axes for that purpose, but we need a work axis on this part. But when we place the work axis, we're supposed to be able to select a cylindrical surface to place the work axis, but there's no cylindrical surface here. it's a extruded hexagon. So what we're going to do is we're going to use the origin. We're going to use the z-axis, right? Which is we centered the hexagon in the sketch on the origin, right? So we know the center of the hexagon is centered on the 0, 0 point of the model. So what we're going to do is we're just going to turn on the z-axis. Now the z-axis is an automatically created work axis. It's still a work axis just like any other work axis. It's just automatically created to be along the z-axis. So we expand this origin folder over here in the browser with this little arrow. We go down to z-axis, we right click on it, we click visibility, it shows up. You can see it's right there, and it's right in the middle of the hexagon, which is exactly what we want. And Inventor automatically scales it, so it's just a little larger than the part, so you can see it, which is nice. We're going to collapse that again, just get it out of our way. Okay, so we're going to set the material for this. I believe it's 7075, and I don't want to go check, so we're going to call it 7075. It's not that critical. We know it's aluminum. Okay, and then we don't want this color, so we're going to go to the Inventor Material Library and find, I guess it's up at the top, I think it's called aluminum flat. Yes, aluminum flat. This is the normal aluminum color. If we use Andy Mark's Hex Shaft, it would be just aluminum. If we use Vex's, it would be black anodized, but it really doesn't matter. We just want it to look reasonable in the model. So we're going to give this a save. We're going to give it the next number in the sequence. It's going to be 3. Now we're going to go back to we're going to close that out. I think we're done with the standoffs. We're going to close that as well. All right, so we're gonna place that part in here, and we're going to constrain it in place. So we hit the place button, we find the file, we open. It's already facing the right direction, so we place it down and hit escape. Next, we're going to constrain. So now we just need to line it up with one of these bearings, right? We don't have to line it up with both because we know the bearings are lined up with each other. So if we line the shaft up with one of the bearings, we know it'll be lined up with the other bearing. So we're going to select the work axis, and we're going to select the work axis of the bearing, and we're going to click apply. Okay, now you notice if we get out of this, this can slide back and forth. It can also rotate, and it looks a little weird, right? I mean, you can see that the hexes aren't lined up, and this part's kind of clipping into the bearing. That's fine. Don't worry about it, especially in the build season. Don't worry about trying to line these hexes up. There's no reason to go to all that work to do that. It doesn't make an effect on the model. Now, if you're trying to do a nice rendering or something, and you're trying to make the model look really, really nice and really photorealistic, then you could go do the time to do that. But typically, in the part of the season where we're doing renders and trying to make stuff look nice, that's kind of like after all the design's done, so you kind of have the time while the robot's actually being built or programmed or whatever. You have the time to go back in and add these constraints later after everything else is designed. So we're just going to let this free rotate. That's fine. It's not hurting anything. It's an accurate representation of how the shaft can rotate in the final gearbox. The only thing we need to do is we need to line the end of this up with the end of the bearing, because that's how it's supposed to be. So we can do it on either end. It really doesn't matter. I'm going to do it on this end because once again, this is the end that's on the grounded plate. It just makes more sense to me. So I'm going to go to constrain. Now this is going to be a flush constraint because we want to line up two faces facing the same direction rather than attach them to each other. So we're going to click this flush button here. We're going to click the end of the shaft and the end of the bearing and click apply. Okay. All right, so that's that. So let's escape out of this. Now let's talk about something for a second. This shaft, if we build this in the real world, right? Okay, there's going to be screws in here, so this is going to be held together firmly, and we'll add the models of those screws later. But if we put this shaft in, right, the bearing has a flange, right? The bearing can only come out of this hole to the inside, and this bearing over here can only come out of its hole to the inside. But neither of them can do that because the gears are in the way, right? So this bearing here this bearing and these gears are effectively keeping this bearing in, and this bearing and the gears are effectively keeping this bearing in, right? So you can't get the bearings out unless you take the gearbox apart by taking the standoffs apart, right? Or you slide the shaft out and pull the gears out the side. Now, that's a problem, what I just said, is because you can slide the shaft out, right? We just put a flush constraint here, right? That made this shaft, now the shaft can't move back and forth, okay? But in the real world, you don't have flush constraints, obviously. So we have to have some sort of mechanical method of keeping the shaft from being able to slide out either from this direction or from this direction. So there's a few different ways to do that, and I'm not going to go into all of them here. We're just going to talk about the one that we're going to use for this particular case. What we're going to do is we're going to put a tapped hole in each end of this shaft. Okay, kind of a lot like the standoffs, right? It's going to be a 1032 hole. And then what we're going to do is we're going to put a washer here, and then we're going to put a screw into the threaded hole. So you're going to put a screw with a washer, and basically the washer is going to be larger than the hexagon, right? And so that the washer, I'm not sure if the washer will be larger than the corners of the hexagon, but it'll be larger than the flats. And the washer will basically keep the shaft from moving in this direction, right, into the bearing, right, because the washer will catch on the bearing and keep it from moving. And then on the other end, there'll be another tapped hole and another washer and a screw holding the washer in place. That'll keep the shaft from going out the other direction. And then if you want to take this apart, you can just take like this screw and this washer off and then pull the shaft out from this end if you want. So that's a pretty common method. A lot of teams use that. It's very convenient. It's easy to do. It's pretty easy to tap a hole in the end of the shaft. It's very, very fast when you're trying to make parts. It saves a lot of time. It's really easy to assemble, and it's pretty easy to maintain, right? If you need to take this gearbox apart, you don't have to take the whole thing apart. So you can always open a part, right? You can go up and open if you want, and go in and open the part if you want to edit it. You can also right-click on the part in the window and click Open. You can also right-click on it in the browser and click Open. You can also just double-click on it, right? Everything else will gray out, and then you can edit the part in place. You got to be a little careful when you do this, but let's just work on it. So you pretend all this other stuff doesn't exist, right? You're editing the part. This is just like having the part open on its own. So you can just double click on it, edit here if you want. So we're going to create a sketch on the end of the part, and we're going to create a point, and we're going to finish the sketch, right? This is just like the standoffs. We're going to create a hole, and we're going to go through and we're going to select a threaded hole. Our termination is going to be distance. It's going to be a full depth threaded hole. It's going to be a number 10 hole with 1032 threads. Okay, and click OK. Now we're going to go back around to the back side, start 2D sketch. Oops, I made a mistake. I'm going to undo with this arrow, or I can press Control Z, okay, to undo what I just did there, and I'm going to try that again. Sketch on the end. Okay. Then our point right here in the middle on the green dot. Finish the sketch. Create the hole feature. Our settings are all the same, 1032, full depth. Click OK. Alright, then you can click this return button up here to go back to editing the assembly once you're done editing the part. Okay, you'll notice we got our tapped holes there. That's great. You'll notice Inventor does not actually create threads in here. It creates what's called a cosmetic thread, which is basically just a texture. That doesn't hurt anything. It just cuts down on processing speed, and it doesn't, or processor load means that it doesn't have to render as complicated graphics. Makes Inventor faster. So if you wanted to actually model actual threads, you could do that, but there's no reason to. All right, when we go through and we download all the fasteners and put all the screws in, we'll put the screw and a washer in the end of this to accurately represent what's going on there. But for now, we're just going to move on. All right, so let's talk about, save this real quick. Let's talk about the output shaft. We want the output shaft to be 1/2-inch hex, right, which is why this bearing is 1/2-inch hex, and the gear is 1/2-inch hex. And we want it to stick out 3 inches on this side. We don't want it to stick out on this side. We want it to stick out on this side, and that's just the way we decided to do it. There's during the build season when we're designing something, we'll have to make those decisions based on what the gearbox is for. But Now, you'll notice we put a round bearing in here. Let's talk about that for a second. So first of all, there is nothing keeping this bearing in. Right? This bearing can just fall out in the real world. In the CAD, it's constrained, but in the real world, this bearing could just come out. It's going to be a little bit of a snug fit in this hole, but with vibration and load and stuff, it would probably fall out. Also, this gear, there's nothing actually keeping this gear in. Now, if the gear moved in this direction far enough, it would start rubbing on this gear, and that would be a very, very bad thing, right? So we want to keep this gear over to this side. And in addition to that, that will also keep this bearing in. So the bottom line is, up here we had these two gears that were touching each other and touching the bearings on either side that kind of kept this whole thing from moving out of place. Well, down here, it would be nice if we had the same thing, but we only have one gear. So we need something that's not a gear to just fill this space. Okay, we're just going to use a spacer. Now, Hex sells these really nifty products. If we go back to our browser, we go up to hardware, we go down to acetyl spacers. They sell these little plastic things in a variety of lengths, and they have a hex hole in the middle, and they're just plastic. They're just spacers. You put one in there on the shaft, and it takes up space, and it helps space your stuff your stuff on the shaft apart, and it's great. So they've got a few different lengths. Let's go back to our CAD model. Let's figure out what length we need. So we're going to press M to activate the measure tool. We're going to click on the end of the bearing and the end of the gear, and we've got 0.502. Now you remember how I was talking about some errors with I don't want to say errors, some rounding errors specifically with the dimensions of the gears because of how they were exported probably. This is a ½ an inch, right? Same thing as it was up here. So we're gonna use a ½ inch spacer, and that 0.02 of an inch will just be a little bit of slop, or it'll be a perfect fit depending on what the tolerance of the gear is. So we're gonna use a ½ inch there. Those 0.02 aren't gonna be a problem. You could even have a bigger gap. Like really, the spacers are not super critical. You just want to kind of contain the stuff. So we're gonna go down to CAD. And we're going to go to it's going to be ½ inch hex spacer, and it's going to be a ½ an inch. So we're going to go download that, and we're going to show that in the folder by right-clicking on it and clicking that. So click Cut, and then we're going to close out of that. We're going to go to our CAD class Gearbox folder and paste that in there. Now we're going to go back to Inventor, and we're going to import that file. So it is ½ inch acetyl spacer. So we're going to open that up, just like we did with the other stuff. Click OK, delete the extra sketch, place our work axis. We're going to set the material to scroll all the way up to acetyl. Acetyl resin, black or white. The website shows that they're black, so we're going to select acetyl resin black. Now you'll notice the color didn't change, so we're going to do what we did earlier with the gears. We're going to go to solid bodies. We're going to right click on solid 1, go to properties, click the drop down, go up to as part, click clear all overrides, click OK, and all of a sudden the color changes. So that's great. We're going to save that. We're going to go back to our, I think we're actually done with this. We're going to close that. We're going to go back to our assembly. I'm going to close this as well. Okay, so assembly is the only part we got, or only file we got open. All right, so now what we're going to do is we're going to drop this part in. We're going to constrain it in here. So we're going to place, grab the acetyl spacer, place it down, press escape, activate the constraint tool, grab the work axis, connect it to the work axis on the bearing, and we'll just constrain the end of the spacer up against the bearing. All right, so now this can't fall apart. Now we just need a shaft in here. Now let's talk about the shaft for a second. So we could do exactly what we have up here, right? Just if this bearing was a hex bearing instead of a round bearing, and I'll explain why it's a round bearing here in a second. If it was hex all the way through, right, we could just put a screw on either end. But the problem with that is there's something out here, maybe a wheel, could be a winch, could be a sprocket or something to drive an arm, could be anything. We're driving something out here, and that's why we want the shaft to stick out of this gearbox, right? We want the shaft to stick out so we can drive things with this gearbox. Okay, but that means that because the shaft is sticking out, we can't put a screw and a washer on the end to hold the shaft from being able to move in and out like we could with this shaft, right? Because this shaft is flush with the bearings on either side. With this shaft, it's only going to be flush with this bearing on this side, and it's going to be sticking out here. So if we put a screw and a washer on this side and on the end over here, we could slide the output shaft this direction, right? But not the other direction, which is kind of half what we want, but we don't want to be able to slide the shaft at all. So here's what we're going to do. We're going to have a 1/2 inch hex shaft. The 1/2 inch hex shaft is going to be outside of the gearbox by 3 inches. It's going to go through this bearing, 1/2 inch hex, through the gear, 1/2 inch hex, through the spacer, also 1/2 inch hex. And then what we're going to do is we're going to use a lathe, and we're going to turn down just the last little bit of the shaft, the part of the shaft that's in this bearing, to be round instead of hex. So it's 1/2 inch hex out here, and we're going to turn down, we're going to use the lathe to basically cut off the corners of the hex, basically, and turn it into a circle. And it's going to be 1/2 inch round going into this bearing. Now what that does is when we turn it down in the lathe to round, we're going to have basically little corners, right? Where the corners of the hex are, there's going to be little corners. And when we model this part, if you don't understand that, you'll see there'll be a visual aspect there. But the corners will basically, the corners won't be able to go through this bearing, right? So if the shaft wants to slide in this direction, right, the corners will form a little shoulder, and it won't be able to move, right? And then we'll put a tapped hull and a washer on the back side, and that will keep the shaft from being able to move the other direction. So that will constrain the shaft in both directions, and then this gear and this spacer will keep the bearings in their places, and everything will be happy. So we need 3 inches of shaft outside the gearbox. We need enough hex to go up to this bearing, and then we need a little bit of a round bit. So let's take some measurements here. Let's use the measure tool with the M key. Measure from the face here to this. So that's 1 5/16, which makes sense given our other measurements. So 1 5/16, and then we need 3 inches on top of that. So let's create a new part here. Go to standard.ipt. All right, we're going to create a hexagon just like we did before. So create it on the center point, then F9 to hide the constraints, then vertical constraint on the sides so it can't spin, then a dimension to dimension the width, and this is going to be 1/2 inch, right? 1/2 inch hex, not 3/8. All right, so that's that. We're going to finish the sketch, and we're going to extrude it. So this is going to be, now I mentioned it was, so we measured, it was 1.313. Now I know for a fact that that's supposed to be 5/16, and Inventor is just rounding the last digit, right? So it's 1 5/16, which is actually 1.3125. Okay. Then we want 3 inches outside of the gearbox, so we're going to do +3. Okay, and that's, we'll let Inventor do the math for us. So we click OK. All right, so now this part's going to be outside the gearbox. This part's going to be in the bearings and such. Then we need, on this end, we need a round part, right? So that's going to be from the front of the bearing to the back of the bearing, right? We know what that is. That's, we can go and look that up on Vex's website, but I know what it is off the top of my head. So it's going to be 5/16. So we're going to go to the back. We're going to create a sketch, right? We're going to create a 1/2 inch circle, okay, 0.5, press enter, excuse me, and then we're going to finish the sketch. We're going to extrude it out, and it's going to be 0.3125, right, which is 5/16, or you could do 5/16, okay? Click OK. All right, so remember what I was talking about earlier. So this is going to start, the whole thing is going to be a hexagon. Then we're going to put it in a lathe. We're going to use a lathe cutting bit. We're going to spin this up, and we're going to cut this down. So then these little faces right here are going to be left over, and these are what's going to stop the shaft from being able to go through the bearing and slide out the back of the gearbox, if that didn't make sense earlier. So now we can create a work axis. We could use the origin thing like we did on the other hex shaft, or we can just use this cylindrical surface, which is probably what I'll do. So there's our work axis. We know there's going to be a tapped hole back here, so let's go ahead and create that. So let's create a sketch on the end here, and create a point, and finish the sketch, and create a hole. So let's talk about hole size here for a second. Just from experience, right? We do this every year. You know, all of our robots have shafts that have tapped holes in them. Now, I know for the 3/8 hex shaft that we used on the cluster shaft, I'm going to exit out of this for a second to show. So this is a 1032 hole in this 3/8 hex shaft. The washer, a standard washer for a 1032 is big enough to stop this shaft from being able to move through a bearing. However, a washer for a number 10 fastener is smaller than a 1/2 inch in diameter. So putting a number 10 on this backside with a washer wouldn't do any good. We could use a really big washer, but you know, we don't stock those typically. We would have to buy it special, and there's no reason to do that. Because what we can do is we can go a size up, and instead of using a 10 fastener, we can use a 1/4 inch fastener, and the washers for a 1/4 inch fastener are large enough. And those are fasteners we got, you know, tons of them laying around. Most teams do. So typically, a lot of teams do this. Typically for a 1/2 inch hex shaft, people use a 1/4 20 fastener instead of a 1032 fastener. So we're going to create a hole, and we're going to create a tapped hole, and the size is going to be 1/4 inch, which is selected by default. The designation is to be 1/4 20, which is selected by default. We're going to just tap it as deep as we can go, even though we don't need all 3/4 of an inch. We'll just model it that way. We'll click OK. All right, so that should work out just fine. So we're going to select, go up, and select aluminum 7075. We're going to select a real aluminum color, aluminum flat, and I'm going to save this, give it the next number in the sequence. Okay, so we're done with that. We're going to go ahead and constrain this in place. Place it in, place the shaft down, press escape, go to the constraint tool. All right, so the first thing we're going to do is we're going to constrain the center line of the shaft to the center line of this bearing. Okay, we're going to get out of the constraint tool. So now, once again, this shaft will be able to spin just like all the others and just like the gears. We need to attach one of these little faces to this bearing here. Now, we can't get to this like surface in here that we constrained to before. So what we're going to do is we're going to disable this part, right? We can't move this part, but we can just turn it off so that it can't be selected, and then we can go ahead and select. So if we go in here, we click on it, we right click, and we go all the way down to enabled, and there's a check mark here, and you uncheck it, right? It turns transparent, and I can't click on this part anymore. I'm clicking, but I can't select it, okay? So what I can do now is I can click the constraint tool, and just select one of these little faces and go back around and select the front of the bearing. Okay, and that's the constraint I want. And now the shaft can spin, but it can't move left and right, which is perfect, right? And you'll notice it's nicely flush to the back, which is what we wanted. Now you'll notice this part here, the spacer, this little icon turned green when I disabled it. So it's easy to find in the browser which one is disabled, because you can't hover over it and highlight it in the browser now. So if you have 100 parts in here or something, it's pretty easy just to look and see, okay, which one's green, and when you hover over it, it'll show what it is in the viewport. So if I hover over this, you see a highlight there in the viewport in the middle of your screen. So if we right click on it here and click enabled, it'll show back up, right? And now it's selectable, and the green goes away. Okay, excuse me. All right, so this is it, right? This is the important part of the mechanical gearbox, right? We're going to go through and we're going to add all the fasteners in the next video, and that will bring the gearbox up. It'll give us an accurate weight if we have all the fasteners in there, and it'll show us what types of fasteners to use and all that. So just a quick note about the fasteners: we don't always put fasteners in our CAD models, and the reason for that is, if you're looking at the CAD model and you see that there's a shaft with a tapped hole in the end, you typically, anybody that looks at that knows how the robot's put together will know that there's supposed to be a washer and a screw there. Okay, and so typically it saves a lot of time to not put fasteners in the CAD model. Also, having less parts in the CAD model saves some processing and rendering power, so it helps Inventor not lag when you're working on large assemblies. So we don't always put fasteners in CAD models. That's pretty common. A lot of people don't. However, it is good practice, because occasionally certain mechanisms might hit fasteners and you won't realize it until you see it in CAD. Like, for instance, here's a good example. We've got screw heads that are attaching this motor. Well, I know that it's far enough away that those screw heads won't hit this gear, but you could get yourself into situations where screw heads would hit a gear, right? Or something, or if there were belts or something. So you want to be careful. You don't want to omit fasteners from a CAD model unless you know for sure that they're not going to interfere with anything. If you're not sure that they won't interfere with something, you should put up in the CAD model to make sure. That's just good practice. That'll help you not run into problems with your designs once you start building it, because it's so much easier to correct stuff in CAD than it is to build half of an assembly, realize it interferes with itself and stuff runs into each other, and you've got to try to modify it and fix it on the fly. So that's going to be it for this video. Give that a save. Next video, we're going to put all the fasteners in. We'll download those, constrain them all, and we'll have a finished product. Thanks for watching.